All right, so section 4.5 covers graphs of sine and cosine functions. So this is not needed for any of the problems on the assignment, but this does come in handy when you move on to calculus, which is why I'm covering it. So 4.5 covers sketching the graphs of basic sine and cosine functions, using amplitude and period to help sketch the graphs of sine and cosine functions, sketch translations of the graphs of sine and cosine functions, and then using sine and cosine functions to model real-life data. Now, all these sketching parts, we're going to use Desmos for that. We're not going to really worry about having to sketch it by hand. So what's important is understanding the terminology and then being able to model real-life data with the values that you have. So we're going to start with looking at what sine and cosine look like when you have them graphed on the rectangular coordinate system. So I have two graphs here. The top one is sine and the bottom one is cosine. So you can see that their shapes are very similar. They basically have a pattern that goes on forever. And the difference between the two is that sine starts at the origin, essentially. It's always going through the origin at 0, 0, while cosine goes through 0, 1. So that is the difference. So you can see that they're shifted by pi over 2. So you can look, we have our x-axis whenever we're doing sine and cosine, because we're using trig functions, we're looking at the unit circle, which is 2 pi. We always look at a period of 2 pi. The period is basically just when does it start repeating again. And then we typically divide that up into 4 sections. So you can see that for both sine and cosine, they both have a range from -1 to 1, although this can be changed based off of transformations to these graphs. Now, sine is considered symmetric with respect to the origin, which makes it an odd function. And then cosine is symmetric with respect to the y-axis, which means that it is considered an even function. So if we focus on just the period, which is from 0 to 2 pi, you can see the key points of sine curves, and this is usually what we use when we're graphing sine curves by hand. And again, we'll just use Desmos, but if you do choose to do it by hand, these are the points you're looking at. So you're always looking at your y-intercept, which is either 0, 0 for sine or 0, 1 for cosine. Then you're looking at where the maximum and the minimum points are, and then where your halfway points are between each of those. And they are different depending on which curve you're looking at, because they are shifted by about pi over 2. But if you know these key points, then you can use this to graph pretty much any sine or cosine function. All you need to do is then apply the transformations to these key points, and then that will get you your new function. So when we're talking about transformations, we have to look at our basic sine and cosine graphs. And so for sine, it's y equals d plus a times sine of bx minus c. And then for cosine, it's just cosine instead of sine, but everything else stays the same. So the value in front of the sine and cosine, the value of a, that it does a vertical stretch or shrink. That is the same thing that happens when you have a in front of any function. Like if you have ax squared, that a would be a vertical stretch or shrink. So the transformation aspects are the same regardless of whether you have a traditional function or a trig function. Now, the absolute value of a is what we call the amplitude of a trig function. And amplitude is half the distance between the minimum and the maximum values. That's important for when you go on further when you're modeling. Now, inside the actual function, we have bx minus c. So in college algebra, we generally don't talk too much about horizontal stretch or shrinks, but if you have a value in front of the x, that does a horizontal stretch or shrink. It's less important with functions like x squared, x cubed, the square root of x, because you don't really notice that as much. But with trig functions, it actually does make a big difference, because this basically changes the distance from when we start repeating our pattern again. So b is representing that stretch or shrink horizontally, and 2 pi divided by p gives us the period. Or 2 pi divided by b, I'm sorry, I said p. But that is what the period, and the period is what we call the distance from when it starts repeating. Now that minus c, if you remember from transformations in college algebra, if you add or subtract anything to x, it shifts it left or right. So that c shifts left or right. It's a horizontal shift left or right. But because we have a value in front of the x, we actually have to take that in account. So the shift is really by c over b. If b is equal to 1, then we're just moving left or right by c, but it's really c over b. When we have trig functions, that is what's called the phase shift. So when I say that cosine is shifted from sine by pi over 2, that's a phase shift. And so if you're trying to figure out what the interval is for one cycle, or basically the period, you can use that phase shift to figure it out, as well as the period, and you can figure out where you start and then where it starts to repeat again. Now the last part is d. So d is a vertical shift up or down. Just like with regular transformations, if you add a value to your function, it moves it up or down. So we have a vertical shift up or down here, and that, when we have trig functions, is usually considered the midpoint of the maximum and minimum values, because a trig function is basically centered at 0, and then you have a max and a min, the value of the amplitude above and below. So if it's shifted up 5, your new center point is going to be 5, but you're going to have values above 5 and below 5 based off of that amplitude. So when you're graphing trig functions in Desmos, you can just type it into Desmos like you would type in any other function. If you type in sine, cos, tan, you use those abbreviations. Desmos knows what you're trying to graph. Just make sure that you put parentheses around anything that's involved with the x in case you're having shifts or stretches and shrinks there. You do want to make sure, though, that your horizontal axis is in the right divisions. So if you click the wrench, you can get options, and then you can actually change your x-axis, and you can type in from -2 pi to pi. And you just type in the letters pi, the word pi, in order to get the pi symbol. So you don't have to try to write -3.14. You can literally just type in pi, and it will do it for you. You also want to make sure that you're in radian mode, because whenever we graph trig functions or work with trig functions, we always default to radians. So you want to make sure that you have radians on, and that is the default that Desmos has. So I'm going to demonstrate all of these terms basically with some modeling. So this is actually a problem from the textbook from section 4.5. It's number 83. And the table shows the percent y in decimal form of the moon's face illuminated on day X in the year 2018, where X equals 1 corresponds to January 1st. So we're doing 5 things here. First, we want to create a scatter plot of the data. Now, I actually did this already for you, and I included the picture. And while most scatter plots, we don't connect the dots, I connected them so you can see the shape to help you determine whether it's going to be a sine or a cosine function. And part B is to find a trigonometric model for the data. Then C, you want to graph the model and the data together. And that's to see how well the model fits the actual data. Then for D, what is the period of the model? And we will actually answer D as we answer B. And then the last part is to estimate the percent of the moon's face illuminated on March 12th, 2018. So when we start this off, we have to decide whether we're going to use a sine or a cosine function. So if you look at that graph, you notice that we start, our very first point is at a peak, and it's at a value of 1. It's basically at a high point. So if I go back to my graphs of sine and cosine, cosine also starts out with the peak. You can see in the dark black line there that the very first point that we have graphed is at the peak of the graph, while sine starts at 0. So if you have something that starts at the peak, you're going to use a cosine graph. So even though we don't start at 0 for our function, our first value is at 1, we're still starting at the peak, we're starting at the maximum, so we're going to use a cosine function. So I always start off by just writing down what the actual function is that I'm trying to fill in here, just so I know all the values that I have to find. So we've decided that we need to use cosine. So this is y equals d plus a times cosine bx minus c. So you can determine the values of a, b, c, and d in pretty much, you know, they're different orders. You don't have to do them all in the order that I'm going to do them, but this is what makes sense to me. The first thing I always do is find the amplitude, because that's one of the easiest things that you can do. So if we go back to where I defined amplitude, amplitude is half the distance between the minimum and maximum values. So that's going to allow us to figure out what the amplitude is based off of our data. So our minimum value is at 0, and you can see our maximum value is at 1. So you can see that from the table, and then you can also see it on the chart. So those are our minimum and maximum values. So the amplitude is half the distance between there. Now it's pretty easy to figure out what that is when you're just looking at 0 and 1, but I am going to go through all the steps and actually show the math so that if you have something that's not at easy values like that, you can still know what you need to do. So our amplitude is 1/2 the distance between the max and the min. So it's basically max minus min divided by 2. So that's 1 minus 0 for our max minus min times 1/2 or divided by 2. So our amplitude is 1/2. So this tells us that A is equal to 1/2. So the amplitude is always the absolute value. So if you ended up, you just take the absolute value of it. And we got a positive number, we don't have to worry about that. So our A is 1/2. So we've already figured out one value of, you know, that function. Now the second value that I always go to find is the vertical shift, because that is also pretty easy. So if I go back to my definitions, the vertical shift is the midpoint of the maximum and minimum values. So we've already got the maximum and minimum values, which were 0 and 1. Now I just need to find the midpoint of those. So that's where you add them together and then divide by 2. So this is going to be the max plus the min divided by 2. So again, this is really easy with our numbers. So we're just 1 plus 0. And we get a vertical shift of 1/2. So the vertical shift is d. So d is equal to 1/2. So those are the two easy parts to find. B and C are a little tricky, and those involve first figuring out what the period is. And then once you figure out the period, then you can figure out B and C. So I'm going to go back to my definitions. So the period is what we call the horizontal distance between the repeating values. So we're looking at our x values and looking for that distance from when they start repeating. So I'm going to go back to the chart here. And if we start out at 1, we start repeating again at 1 when x is equal to 31. So our period is the distance between an x value of 1 and an x value of 31, because that's when the y value, the highest point where we started, we start repeating again. We're repeating that cycle. So our period, make sure I switch to my black ink here. So this is the distance for that between 1 and 31. So first I'm going to just indicate this, that we repeat the pattern at 31, 1 as our ordered pair. And we started at 1, 1. I'll go back to that table. So we see we start at 1, 1, and then at 31, 1, we repeat it again. So our distance between these 2 points is just going to be 30, because 31 minus 1 is equal to our period. And so our period is 30. And if you're wondering about units, that's 30 days. So this pattern repeats every 30 days, which in real life we know makes sense, because we say this is where months come from, basically, as the cycles of the moon. So we found our period of 30 days, but our goal is to figure out B and C. So I'm going to go back to my definitions. So first with B, 2 pi over B is called the period. So the period equals 2 pi over B. So I can use that relationship to solve for B. So 2 pi over B will equal to 30. So if I multiply both sides by B, I get 2 pi equals 30B. And then I can divide both sides by 30. And I'm going to get 2 pi over 30. And then we want to reduce that. And that reduces to pi over 15. So all I had to do was solve that. And then that gives me B. So B is equal to pi over 15. Now we also need to use the period in order to find C. So if I go back to my definitions, we have C over B, which is the horizontal shift left or right. And then we have the interval of one cycle is C over B to C over B plus 2 pi over B. So we know that one cycle starts at 1 and then it goes to 31. So I can say C over B equals 1 because I know what that period is. Or if you wanted to, you can use the right side and you can say 31 equals C over B plus 2 pi over B. But that's a little more complicated. So I'm going to just do this in a different color. We know that C over B is equal to the first point in our cycle, which is 1. And we've already solved for B, which is pi over 15. But it might be easier to just multiply both sides by B and see that C equals B. And so then we can see that since B is pi over 15, C is also pi over 15. That is not always true. It's only true in this case because we started at an x value of 1. If you started an x value of something else, then it would come out differently. And if you started with like an x value of 2, then you know that you'd have to solve. So now we have figured out A, B, C, and D, and we have everything we need to actually write the model. So I'm going to go to the next slide, and you're going to plug in these numbers. So it's y equals D, which we found was 1/2, plus A, which was 1/2, times cosine, and then parentheses, we had B times X. So B was pi over 15, so that's pi over 15x, minus C, which also came out to be pi over 15. So that's our model. Now, the next question was asked, and let me go back to it. Let me find the right slide. So it says graph the model and the data together. It says what is the period of the model? We found that already. That's 30. And then estimate the percent of the moon's face illuminated on March 12th, 2018. So we got the model. Let's graph it so that we can see how good of a model this is. So I'm going to pull up Desmos and start graphing. And I'm logged in. I actually went ahead and saved this already, so I didn't have to worry about typing in all the data again, but you can type in the data And then let me actually change the color so you can see. So our ordered pairs that we're given are in red, and then the model is in blue. So you can see while it's not perfect, it does a pretty good job of fitting our model. So it doesn't quite get it on the halfway points here where 50% of the moon is illuminated. It's a little bit off, but it does make sure that it hits on the maximum and minimum values. And so it's pretty close for a model. Okay, now getting to the last part, we want to estimate the percent of the moon's face illuminated on March 12th, 2018. So we were told that X starts at January 1st, 2018. So we need to know how many days this is. So I know that January has 31 days. February is not a leap year in 2018. So that means there was only 28 days. And then for March 12th, that's 12 days. So we're going to add all of these up so that we can find out what day of the year March 12th was. So 3, 4, 5, 6, that comes out to 71. So X is equal to 71. So if we want to estimate what percent of the moon is illuminated on March 12th, we want to plug in 71 into our model. So Y equals 1/2 plus 1/2 cosine pi over 15 times 71 minus pi over 15. Now let's first do this by calculator, and the one thing you want to make sure that you do is that your calculator is in Radian mode. So if it's not in Radian mode, you want to make sure that you switch it to Radian mode. Like my calculator right now is not in Radian mode, so I need to switch it because we always work with Radian mode when we're dealing with functions. Okay, so I need to do the pi over 15 times 71, and I have a button on my calculator, so I can actually just use the pi button. And I'm going to also subtract the pi over 15. And I'm going to convert these to decimals just because when I take the cosine, I'm going to already have decimals. So the pi over 15 times 71 minus pi over 15 comes to 14.66 roughly. There's several other decimal places, but I'm just rounding to 2. So now I want to take the cosine of 14.66. So I have y equals 0.5 plus 0.5 times, and this comes out to basically a negative 0.5 if I round it to 2 decimal places. So I have y equals 0.5, and then 0.5 times negative 0.5 is a negative 0.25. So then 0.5 minus 0.25 is 0.25. So our estimate is 25%. Now, since I have this graphed, what's really nice, if I go back to Desmos, if I put it in function notation, so I had written it as y here, but if I put it in Desmos with f of x, then I can use f of x and use Desmos to find the value for me. So if I plug in f of 71, that gives me 0.25. And I can even scroll, and I can even make this an ordered pair by typing in 71 comma f of 71, and you can see where it shows up on our plot, and that's where the 0.25 is, or 25%. And you can zoom out if you want to see. You can see that the trig function, like cosine here, it just keeps going on forever. It just repeatedly cycles. It doesn't really end or anything. So that's basically everything you need to know about section 4.5. When you go on to 4.6, you learn about like tangent, cotangent, those other types of functions. Again, you can use Desmos for graphing. What's important is understanding the different aspects of it and then how to create an equation based off of the data, because that will be helpful when you go on to calculus, especially when you start doing derivatives and things like that. So if you have questions, you guys know how to reach me, and I will talk to you later. Bye.